Hello and welcome. In continuation with our previous lecture of complexometry, we have discussed about masking or screening which is required, wherein some metals tend to interfere in complexometric titrations, that is titrations with EDTA, and these metals have to be removed before the titration proceeds. And the physical removal of a metal is not possible from a solution, so a masking agent is added to prevent the reaction of one substance, or as we say, one metal ion with the other substance. And after the masking agent has been added and the titration has proceeded, demasking needs to be done, wherein the prevention of the action of a masking reagent by a further reagent, which is termed as demasking. And masking or screening of metal ions can be followed by various methods, in which adjustment of pH, complex formation, we have already discussed in our previous lecture. Moving on to the next method of masking or screening of metal ions, which is by precipitation. This process can be used in those cases where the solubility products of some precipitates are very low, even in the presence of EDTA. Such metals can be masked by forming precipitates. For example, if calcium needs to be estimated by EDTA in presence of magnesium, then magnesium can be precipitated in the form of its oxalate. Similarly, if magnesium needs to be estimated in presence of barium, then barium can be precipitated in the form of its sulfate or chromate and be masked hence. If calcium needs to be estimated in the presence of magnesium, as in case of hardness determination, then magnesium can be precipitated as its hydroxide, which further won't interfere in the titration of calcium with EDTA, using eriochrome black tea as the indicator. Another method for masking or screening of metal ions so that they do not interfere in the titration of another metal ion in its presence is oxidation and reduction. In this method of masking, the metal ion is either oxidized or reduced, that is, converted into a state where a weaker EDTA complex is formed or no complex formation takes place, that is by oxidation or reduction of the metal ion. For example, if the titration is done in an acidic medium, the addition of ascorbic acid converts ferric ions to ferrous ions, and the stability constant of EDTA complex of ferrous ions is lower than that of ferric ions. Hence, the interference due to the iron can be removed. That is, if both Fe3 and Fe2 are present in a solution and one of them has to be determined or estimated, then ascorbic acid needs to be added, which changes the stability constant of one of the complexes with EDTA and masks it. Interference due to chromium can be removed by oxidizing it into chromate with hydrogen peroxide. Chromate ion does not complex with EDTA. So, if chromate ions are present, or rather chromium ions are present along with any other ion, and that particular ion, for example iron or nickel, has to be estimated, then chromium ions can tend to interfere. In that case, chromium is converted to its chromate and chromate does not react with EDTA. Similarly, ascorbic acid reduces Hg2, that is mercurous ions, to elemental mercury, which does not interfere in the titration of a particular metal ion with EDTA. Moving on to the various types of titrations which can be performed as in with EDTA or as in complexometric titrations. The first type is the direct titration. Direct titration, also called simple titration. The metal ion solution to be estimated is taken in a conical flask and the indicator is added and the pH conditions are maintained by adding a buffer. Then it is titrated with EDTA from the burette until the color changes towards the end point. So it's a kind of a simple titration wherein simply a solution of a metal ion is titrated with EDTA using a particular indicator. But there are certain limitations associated with direct titration of a metal ion, and those are the absence of a suitable indicator to give a suitable color change. In some cases, a particular metal ion which needs to be titrated with EDTA does not have a suitable indicator to form a complex with, which can give a suitable color change towards the end point, and hence the end point is not easily detected. So one doesn't know when the reaction is complete. Another limitation with respect to direct titration is that it may not be possible to keep the metal ion in solution due to precipitation. There might be some agent, some precipitating agent which might be present or in the solution which might precipitate the metal ion. The rate of formation of metal EDTA complex may be slow, and if this happens, then a large volume of EDTA will be required to complex with the metal EDTA, and the metal indicator complex will not break easily to form the metal EDTA complex. Another limitation is where the metal ion need not form a stable complex with EDTA to enable the titration, and once a stable complex with EDTA and the metal ion does not form, the titration will henceforth not proceed. Another type of titration in complexometry is back titration. In case there is no suitable indicator or the metal EDTA complex is not sufficiently strong, back titration needs to be done to estimate the metal ion. In this method, a known volume of EDTA is added in excess to react with the metal ion to be estimated. Then the indicator is added and the excess EDTA, that is the EDTA left after the metal ions have complexed with it, since it has been added in excess. So whatever EDTA was required to form a complex with the metal has formed a complex with the metal, and the remaining EDTA which has been added in excess is left out. So whatever EDTA is left out is back titrated with a suitable metal ion solution. That is, a metal ion solution is taken in the burette and the EDTA which is there in the conical flask is titrated until the indicator changes from the free state to the metallized color. The amount of EDTA added in excess is to be taken into account in the calculations once to determine the amount of the particular metal ion. Another type of titration is replacement titration. It helps to overcome the difficulty in direct titrations where the stability of the metal complex formed with EDTA is less. That is, if in case of a metal complex being formed with EDTA is weak, its stability is less, then to overcome that problem, replacement titrations are performed. The replacement titration is allowed to proceed, and then the replaced ion is titrated directly, as in the equation below, where M plus Ny is giving My plus N. Here M is the metal ion to be estimated, which due to its weak complex with EDTA cannot be titrated directly, and N is the metal ion which can be titrated directly. So Ny, that is the N metal, is forming a complex with EDTA, and then reacting with M metal, in which a replacement is carried out, as a result of which M metal forms a complex with EDTA and N is released free in the solution. So, just like we have displacement reactions in inorganic chemistry, similarly we have replacement titrations in complexometric titrations. A complex of metal N is added in equivalent amount of M, that is both M and N have equivalent amounts, and after the completion of the reaction, the amount of N released is titrated. And as we remember that N is a metal ion which can be titrated directly, M is the metal ion which cannot be titrated directly because it forms a weak complex with EDTA. So, the amount of N released then after the replacement is titrated, which is equivalent to the amount of M. Suppose if calcium needs to be titrated with EDTA using iriochrome black tea as the indicator, then a small but known volume of magnesium EDTA complex, suppose 2 ml in a 10 ml solution, needs to be added, since the endpoint with iriochrome black tea is not very sharp for calcium. So, if a calcium ion solution needs to be estimated for calcium ions, then if we are using iriochrome black tea as the indicator, then calcium iriochrome black tea complex, or as we say the calcium indicator complex, is very weak and it breaks as soon as it reacts with EDTA. So, as a result of which the endpoint is very sluggish. To observe a sharp endpoint, magnesium EDTA known volume of the complex is added and the titration is proceeded in that manner. The reason for addition of magnesium EDTA complex is, as we say, that the calcium EBT complex is not very stable and breaks upon the addition of a small amount of EDTA. EDTA is an organic compound, so is insoluble in water. For titration purposes, its aqueous solution needs to be made. For this reason, disodium salt of EDTA is taken, since sodium salts of all compounds are soluble in water. Hence, the disodium salt of EDTA can be made into an aqueous solution or can be dissolved in water. Standardization of EDTA, that is determination of the exact strength of EDTA, is done using a magnesium or zinc salt, and a solution of either magnesium sulfate or zinc sulfate is made and is further used for the titration or standardization of EDTA. In complexometric titrations, an important criteria which needs to be followed is the pH control. So, in EDTA titrations, the solution in the conical flask which is to be taken, that is the metal ion solution, the metal which is to be estimated, along with the indicator and the buffer, becomes acidic as the titration with EDTA proceeds due to the constant release of H plus ions as shown by the following equation. The H2Y2 negative is the formula for EDTA, which is having 2 dissociable protons. It reacts with a dipositive metal ion, which can be magnesium, zinc or any other metal ion which can be estimated by complexometry. Upon the reaction, My, that is a metal EDTA complex, is formed and protons or H plus ions are continuously released in the solution. And as we know, the release of protons is resulting in the increase of the acidity of the solution or a consequent decrease in the pH of the solution. The below figure shows us the color changes which occur in the titration of any dipositive metal ion with EDTA using iriochrome black tea as the indicator. The conical on the left shows a metal indicator complex which is pinkish red in color, and upon the titration where the metal ion complexes with EDTA and the indicator, that is EBT, or iriochrome black tea is set free in the solution gives a blue color towards the end point. So, from red to blue we can detect the end point and determine the amount of magnesium or zinc or any other dye positive metal ion present in a particular solution. The indicator used in a particular titration gives a color change in the pH range 8 to 10, and this indicator specifically here we are talking about is iriochrome black tea. Hence, the indicator will not work if the solution is acidic. To enable the indicator to give a color change, buffer solution is added. This buffer is a solution of ammonia dissolved in or mixed with ammonium chloride, and it increases the pH of the solution and maintains it too. Why do we say maintain of the pH is important? Because the pH is constantly decreasing throughout the titration process, which is evident from the equation. So, to maintain that pH, first of all increasing the pH because the pH has decreased due to the release of protons, and this, since the process is continuous ongoing process, so the maintenance of the pH is also necessary to a range of 8 to 10. For that, buffer needs to be added. When we talk about the indicator, which is generally iriochrome black tea as we say for most of the metal ions which need to be estimated, a solid dilution of the indicator needs to be used. Generally, solutions of indicators like iriochrome black tea are not stable. So, a solid dilution of the indicator is used. That is, solutions of EBT are prepared, are decomposed over a period of time. So, generally a solid indicator is preferred. For this purpose, EBT is mixed with a pinch of sodium chloride in the solid form. In this way, the amount of indicator used in the titration to form the metal complex will be less, and sodium chloride will not interfere in the titration. Moving on to the examples of direct titrations, metal ions like magnesium, zinc, lead and manganese can be titrated directly with EDTA using iriochrome black tea as the indicator. Metal ions like calcium, copper, nickel can be titrated using muroxide as the indicator, and the structure of muroxide is given in the adjoining figure, the top figure, and the structure of EBT we have already discussed in our previous lecture. Bismuth can be titrated using pyrocatechol violet as the indicator, and the structure of pyrocatechol violet is given in the adjoining figure. So, if we consider the examples of the direct titrations, for example, in the case of magnesium, if magnesium has to be titrated directly with EDTA, then this titration is a slow reaction at room temperatures. For this purpose, the solution of magnesium should be heated to increase the speed of the reaction. So, before the titration starts, in the conical flask where we take the magnesium solution, we add the indicator, that is iriochrome black tea, and we add the buffer to maintain the pH. After that, the solution of this magnesium ion is heated first so that the speed of the reaction increases, and after this the titration is performed. So, the procedure goes as follows: the 10 ml of 0.01 molar of magnesium sulfate, for example, is taken in a conical flask. To this, an equivalent amount of buffer solution is added, and as we have discussed, the buffer solution is a solution of ammonia and ammonium chloride. Then a pinch of the indicator is added, and that indicator is in a solid dilution form, that is indicator mixed with sodium chloride. The color of the solution, the moment we add the indicator to the metal ion solution, turns red due to the formation of the metal indicator complex. This solution is then titrated with EDTA from the burette till the color changes to blue. The volume of EDTA consumed in this titration gives the amount of magnesium ions present by a set of calculations. And as we have just seen, the color of the solutions which changes from red to blue, wherein the red color is due to the magnesium indicator complex and the blue color is due to the free indicator. The complex which has formed, that is My or magnesium EDTA complex, which has been formed, is colorless. So the blue color is due to the free indicator and not due to the metal EDTA complex. Now 1 ml of 0.01 molar EDTA is equivalent to 0.2731 milligram of magnesium ions. By a set of calculations, we can find out how many magnesium ions are present or the concentration of magnesium in a particular solution. So if the magnesium solution is acidic, then it has to be neutralized first with sodium hydroxide before adding the buffer. Although buffer is alkaline, but that buffer is not sufficient to neutralize the acidic magnesium solution. So NaH needs to be first added to neutralize the solution. To check the neutralization, methyl red indicator can be used as the acid base indicator, and as we know that methyl red indicator is an indicator which is used generally in acid base titrations with a weak acid weak base or weak acid strong base. Applying the same procedure, other ions can also be titrated. However, in case of ions like lead can precipitate as lead hydroxide in the presence of ammoniacal medium as provided by the buffer. To prevent this precipitation, the addition of tartrate ions becomes necessary. The lead tartrate complex formed is sufficiently stable to keep the lead ions in solution, but not stable to prevent its reaction with the indicator and with EDTA. Hence, tartrate is called the auxiliary complex former. So in this case, lead which forms a complex with tartrate ions is very stable and it keeps the lead ions in solution, but it does not prevent its reaction with the EDTA complex or and helps in the formation of the metal EDTA complex. Therefore, it is called the auxiliary complex former, or rather not a direct complex former, an indirect complex former. Thank you.